1, comma 1, comma 0, and over root 2. Right? So that's definitely hard. And one of the things you have to do is you have to draw the picture, have any hope of getting it right. And what's hard about it is picking off and actually keeping the components straight. Right? Not an easy one. The last one is actually, of the three of them, the easiest one. Actually, maybe the first one is the easiest. The second one is definitely not easy. So the last one asks, what is the voltage difference VB minus VA between some point A that's at 1 meter and some point B that's at 0.01 meters? So this is asking for a voltage difference, and everything that's kind of gone before is about the field. So the easy way to do this is to say the voltage difference, and let's do, I think since A is at 1 meter, let's do VA minus VB. Although I asked for here VB minus VA, it's a little bit nasty, so we'll have to remember that here we've got the VA minus VB. And that's, of course, minus the integral of the electric field, which we think we actually know. Point straight out, for example, dotted, with an element of path, dr. And we're going to start at a distance of, in this case, B, because here I did VA, that's the end point, that's the beginning point. So this would be the beginning point, which was 0.01 meters away. And we'll choose, actually, did I say it? Yeah, I didn't say where it was. I said from the z-axis. We'll choose that to be on the x-axis. I can always choose, where my x-axis is. I can't choose the z, that's given. And we'll iterate up to 1 meter. And the reason just for choosing this point here is because this is smaller than that. I like to start with smaller values of x. And if I'm going along the x-axis, that means I'm thinking about some point where I'm starting at 1 centimeter, 0.01, and I'm going out to 1 meter. Which way is electric field pointing? If I'm going from here, where's the electric field at this point? Straight out. Right? That's an easy one. And if I'm out here, it's along the x-axis. Right? So in fact, the electric field is just lambda over 2 pi epsilon naught, and I can say x here, and it's in the I hat direction. So this particular one, and that's a choice. You can, as long as you're going from a distance of 1 centimeter further out, you can pick any axis you want as long as it's not the z-axis or any direction you want. And so this whole thing here, then this only has an x component. So when I dot it with here, it'll only pull out the x component. So this minus integral from 1 to 0, that's the electric field in the x direction dx. And I can just erase that. That's lambda over 2 pi epsilon naught x. And you'll recognize this is minus lambda over 2 pi epsilon naught. And then this dx over x is, of course, just a log. And this was 0.01 to 1. So 0.01 to 1. So this will give me the log. Minus lambda over 2 pi epsilon naught. Natural log of 1 over 0.1. And I guess you can plug in for all this stuff. The lambda was from the first part. Epsilon naught's given on the front page. This is natural log of 100. Right? And that would give you VA minus VB. If you do all that, I think I got around, that was minus 23 volts. And the only silly part here was I asked for VB minus VA. So that VB minus VA would be plus 23 volts. And that's not the kind of thing I would have taken off points with, not that far. So this one is a little bit tricky, only because you had to know to choose something simple to do that integration over. I mean, the line integrals are generally harder if you don't specify the path. Any issues about that? Not simple. We worked out some examples like this in class, but not simple. So this was hard, right? Some parts. Certainly the first part was fun. The next two were quite harder. The next one, 3, has 2 parts, both worth 10 points. So that means they're worth quite a bit. It says, suppose you have 2 point charges, one of 5 nanocoulombs and one of 3 nanocoulombs. One's at one position, you notice I get an x, y, z coordinates, it's on the x-axis. Another one is at, it's on the y-axis, and they're both at 30 centimeters. And so this is a case, as with the previous one, where you really want to make a picture to try to keep things straight. And so the first question is, what's the electric force that Q2 exerts on Q1? Right? So this is pretty particular. So let's try to make a picture. I'm thinking of an x-axis, and y-axis, and there's one charge, Q1, which is on the x-axis. So this is Q1, and it's at some distance d along the x-axis, and Q1 was 5 nanocoulombs. These are all the kind of things you want to put on there to keep it straight. And then where's the other one? The other one is 3 nanocoulombs, and it's along the y-axis. So it's up here, and that's Q2, which is 3 nanocoulombs. Okay, and the D was given as, what was it? It was 30 centimeters. So let me write up here, 0.3 nanometers, right? Which is 30 centimeters. So the first one is, what is the electric force that Q2, this guy up here, exerts on Q1? Q2 exerts on Q1. If I were to draw that force in this figure, where would I draw it and which way would it point? Whereas that Q2 is exerting on Q1. They're both positive charges, so which way is that force pointing? That way, yeah, it's down. They're repelling each other. It's on a line. If you draw a line between the two, which would be a smart thing to do, it's directly away like that. And this is a reminder, again, if you can do it, get it pictorially in there, it's very important to do so because it's hopefully a powerful reminder that force is a what? Force is a vector. It has a direction and it has a magnitude. Why you want to sketch these things if you can. So that's the force. And if that's 30 centimeters and that's 30 centimeters, what's this angle? 45 degrees. This is, right, this length. Well, this is a 45, 45, 90 triangle, and this is that's 45 right there. Okay, so we know what? We know the x component is, well, not quite equal to the y component. The y component is going to be negative of the x component. Right? It's got positive x component and a negative y component. Right? So we can say right away that the force is only in the xy direction. It's got some magnitude. We'll just write that as f, which we'll have to figure out. Right? Times the cosine of 45 degrees. And it's got a y component, which is the force times the sine of 45 degrees. Oh, except for, and of course, no z component. Except we got to remember that should have been minus sine of 40. It points downward, right? It's got a negative y component. Right, so that's what I'm looking for. Now, how do I find the magnitude of the force? Got two charges separated by some distance. How do you get the magnitude?
K.
Yeah, it's the other law. Yeah. So Coulomb's law. Got to ask about the laws. You don't have too many laws in this case. So it's the magnitude of force. That is what I'm writing by F. That's equal to the constant K, which is, I think, it's given on here, almost given on here. Charge 1, charge 2 over distance between them squared. Okay. So let's see, this is, the only thing that's a little bit tricky on this is, of course, 9 times 10 to the 9th. We'll keep the units in SI. This was maybe 5 nanocoulombs. Yep. So 5 times 10 to the minus 9. I'm suppressing all the units. Trying to use everything in SI. 3 times 10 to the minus 9. It's on top. And then what's the distance between these two? It's not 0.3 meters, right? That's this distance. So it's the square root of 2 times 0.3 meters. It's the length of hypotenuse. So that's the square root of 2 times 0.3 meters. And then, of course, that's squared. So that's squared. And let's see if you do all that right. I got something like the magnitude is about 1.06 times 10 to the minus 6 newtons. And that would, if you got that far, I'd probably give you full credit. In principle, you should take that number and multiply by cosine of 45, which is 1 over root 2. That'd be